I hope you can hear me. So, welcome back. So,
So
this is the second session of this day we're going to have. We are just waiting for Dr. Mohammad Khan, who will be joining us in shortly. I think he's having a little bit of internet issue. So, I think all the speakers are present. And so, as soon as Mohammad Khan joins, we'll start the session. Isidro is there too. That's good. All right. Just let's quickly just see whether all the speakers are there or not.
Hello,
Hi, Pawan.
thanks for joining. I'm just waiting for Mohammed. I can see him on the speakers list. Mohammed, you just need to turn on your camera and your microphone. You should be able to be on the stage straight away. I can see you on the list.
I hope he can hear us now. I think he's back.
Hello, everyone. Can you hear me now?
Yes, we can hear you. Can you hear us?
Yeah, I can hear you now at last. Okay.
Okay.
Yeah. Can we start our session? I'm sorry about we're already 3 minutes behind now. So I think
That's fine.
Yeah, the first presenter is Ali Al Yaqub. Ali, are you there? Ali? We can't hear you. Isidro, can you hear me?
I can hear you, yes.
All right. So what happened to him?
I can read that there is a problem with the mic from Ali. So this will be in total 20-minute presentations, right?
I think it's 20 minutes, including question answer. So perhaps we'll
Yes.
we'll stop them after 15 minutes and give 5 minutes for question answers.
Yes.
Hello, Ali. I think the problem which I had when I was joined earlier on, you need to come on Google browser, Google Chrome, rather than using Internet Explorer. That was the problem initially I had with the mic. So if Ali, you're using Internet Explorer, please, if you switch to Google Chrome, what you suggest, Isidro, should we move to the other speaker? In the meantime, Ali can sort its problem.
Yes, I think we should do that.
Just hold on. Mohammed, we are just running 5 minutes late, so it's fine. We can just hang around for a little bit time for Ali.
All right. Okay.
And just for general audience, we are just announcing again, if you are having any question, raise your hand if you are attendee, or you can write down the questions in the question answer session. So at the end, it will be read out and the speaker will be allowed to answer those things. And when we go for the presentation mode for the speaker, I request everyone to put their camera and mic off. Thank you.
Thank you. So the next presenter is, are they ready? Salah.
Hello.
Hi.
Hello.
We can hear you, Salah.
Yeah. Could you give me a chance to? Can I present it now? Or is that possible to present it after Ali? Or I have to present it now?
I'm not sure if you can hear me now. I think I managed to solve the problem.
Then I think that Ali can go ahead. Yeah?
Okay. I'm so sorry for that.
No worries.
Okay.
Salah, can you switch your video off, please?
I'm trying to share my screen. Yeah. Hi everyone. I'm so sorry for the technical problem. Ali Ali Yaqub. I'm a research associate at University, and I'm glad to present work on this conference today. And the title of my paper is Investigating the Impact of Human in the Loop Digital in an Industrial Maintenance Context. So,
can you
and the outline of my presentation, at the beginning, I will talk about the motivation of this paper, and the proposed framework. I will the project I'm working on in digital, and this
I'm unable to hear him. Ali, I think we have lost your voice and we can't see your presentation anymore. Are you with us?
Think Ali's internet connection we lost.
So,
I can't see him.
So, Isidro, what should we do now? Should we move to Salah? Anyways.
I
Yeah.
think we should move on.
Yeah.
Catch up with Ali later on.
Yeah. Salah, are you there? Yeah. You can start your presentation, Salah.
Okay. Hello. Did you can see my slide?
Yes, we can see.
Yeah, I can see.
Presenter mode, so you have all the screen in Power.
So, you can see my slides clearly, yeah?
Yeah, but if you just use the presenter mode or slideshow, it will be it will be more visible then.
Screen, that's one. Application. You can see.
But if you use that with slideshow,
Yeah, I'm using the slideshow. You can see it now.
I think you have to go to the presentation mode.
Okay. Just a minute, yeah?
Yeah.
Yeah, you can see it now.
Yes.
yes, exactly. Move on.
Okay. Thank you for attending my presentation today. My presentation is talking about the scheduling, challenging with the MRO operation innovation sector. It started with the contents, talking about the introduction and the research approach, scheduling, challenging, and analysis, and discussion, conclusion, and future of work. Let's go to introduction to give you the idea about the aircraft life cycle. Every aircraft goes the process for 6 parts of the maintenance process, talking about the management and the scheduling work, management aircraft configuration, and contract engine and work on package design, manages spare part materials, contract production planning and the control, contract production planning and control, executing the certified maintenance work. So let's move to MRO company activity, talking about 4 parts: engine maintenance, base maintenance, lean maintenance, and spare and modification maintenance. However, we will describe it more details during this slides. However, the maintenance MRO company faced challenges related to scheduling because of the large number of the maintenance checklists to completing every day, different aircraft type requiring different checklists. Talking about what the researcher used to research approach, you can see the figure. The literature review analysis is talking about the original equipment manufacturing supplier, flight delay, turnaround time, manpower, and maintenance check. Most factors was to focus about most of the papers related to maintenance check was more than 30%. On right hand, you can see the fishbone diagram, how the researcher analyzes the key finding. As you can see, the scheduling problem divided to 6 parts, talking about management, airline operation, airport capacity, MRO surface, maintenance, materials, and the human resource. We'll talk later about original equipment manufacturing and the human resource and the turnaround and manpower factors. original equipment manufacturing supplier, requirement availability of the spare part, and spare part based on the airline company design. As we know, the private aircrafts need own design in terms of the space or the fleets or the seats to make the customer happy. Supplier spare parts and materials on the time without delay. As you can see, the picture shows the hardest for original equipment manufacturing to supply the items for the surface for aircraft. Airbus 320 gives you an idea about 4 factories which located in 4 countries: Europe, UK, and Spain, and Germany, and Spain, and France. As you can see the picture in here, more than 12,000 components need to deliver on the time. Let's move to aircraft maintenance check. We divided as you can see, divided to 2 type of a check: planned check, which is normal, produced by aircraft manufacturing themselves; lean maintenance, or A check, B check, or C check, or D check. I give you an example for the Airbus 320, when and where should be scheduling for the maintenance. Unplanned check, which is the most factors affected the MRO in terms of the operational aspect. Key challenges for the MRO company is caused by the human error, design error, unexpected for components filler, and materials. Let's and then move it to the challenges for the MRO company, talking about the 4 factors which could be increased or reduced: the maintenance scheduling problem, manpower and the flight delays, and original equipment manufacturing turnaround time. Analysis and discussion, talking about the challenging for MRO companies, talking about the manpower. One of the key cost delivery, the lack of the qualification, talking about the experience, and the engine evaluation manpower, inspection and testing structure. The maintenance scheduling affected because of the maintenance operator training and knowledge and environment condition. And move to original equipment manufacturing and maintenance scheduling. You can see the figure how the number of the papers that's the researcher used it, and we divided as for the methodology they use it, but we found this lake the weakness of the methodology that's used. For example, the case study, there is no one mentioned that the fleet size was not considered. The model study used affected by the used all data. Interview study, the problem with them, they maybe consider the recognized original equipment manufacturing affected the MRO. In on the other hand, we can say it might be MRO operator themselves affected the maintenance schedule. Simulation, the limit of the number using the simulation because of the researcher working in different operation condition. Let's move to 2 factors to talking about flight delays and around turnaround time. As you can see in left right hand, the figures which use the papers, how many the papers and the models that use it. As you can see, the models more than 50%, and in terms of the flight delay. On the other hand, the turnaround time, you can see the model as well used more than 50%. The case study limitation, the number of the limitation and the large volume of the maintenance reports comes every day, and sometimes it's not available. Models study may be always possible and particular, but the large number, as what I said to you, you have to divide it each type of aircraft and then use it to analyze the model. It's hard to control it. Interview In terms of the interview, so the problem comes from an efficient operational strategy rather than to talking about the flight delays because of the surface. Also, the simulation study increasing the number of the flight delay per day. It's been and the turnaround time and the flight turnaround time becomes shortly. You can see the different airline operation as a long haul operation or short haul operation. I give you this previous idea. Short haul operation is talking about, for example, the aircraft take off from Heathrow to Manchester, but long haul operation from the aircraft take off from Heathrow to Hong Kong. That's the meaning for the simulation study. It's hard to use it in this process. Analysis and discussion. For the manpower. Manpower is the case problem that's faced the maintenance of the MRO company, because as you can see, the strategy always conclusion. The maintenance strategy. Each airline, each MRO companies has different strategy, so it's hard to control it. And in terms of the model, the researcher uses the manpower factors. They don't put like the planning system, how the shift work in this company work, so it's hard to use it. Interview not always be useful, because when you ask the question for the for the professional MRO operator service, it might be take the answer based on the current situation and the current situation. Simulation study, limited number of the publication, they don't use it yet, and the lack of, they don't know the number exactly, how many number of the aircraft need, how many number of the manpower needs to service one aircraft. Key finding: original equipment manufacturing and maintenance scheduling. Most of the operation problems for the MRO companies comes from the maintenance schedule and original equipment manufacturing, meeting the deadline and efficient utilization for the resource and repay response. And the change is demand because of the maintenance environment. So the utilization is talking about the type of aircraft, what's type of the maintenance scheduling you need to service, A or C, or heavy maintenance, as a light maintenance or heavy maintenance. A flight delay and the turnaround time working together. The large volume of the maintenance report, aircraft type, and the large number of the aircraft contributed the flight delay turnaround time. The delay pressure involved adhering the maintenance checklist and meeting the time deadline of the maintenance experimental flight delays. Processing as well, an advanced job may arrive anytime. You're not expected the maintenance scheduling. You're not expected as a MRO operation company. The competition between the airlines company itself and the demand for the air travel, increasing the number of the flight scheduling per day, and the flight turnaround time has become shortly. Manpower caused by three elements: parking in place, talking about the layout for the design for the airport, that's and aircraft hangar itself. The time conception to surface the aircraft started with the day which has started and the end, and the skills, how they the maintenance operators deal with the surface because of the overall the maintenance work. Problem facing the maintenance company is estimating. That's the key point, is estimating the number of the operator need to work in company. Operator requirement, multitask in different area, execute from the MRO company, which will affect the maintenance project strategy. Conclusion and future of work. The key challenging when the scheduling MRO is talking about the manpower, original equipment manufacturing, and the flight delays. When manpower issue, the result increase the turnaround time. The flight delay can be caused by the maintenance operator because of their limitation, skills, and knowledge, and the lack of training. Unexpected, the aircraft component failure made the aircraft stay longer on the ground, increasing the turnaround time. As a result, for increasing the turnaround time, original equipment manufacturing supplier performance and the capacity for the supply spare parts and materials time without delay. To design one element, it might be take 6 months to design it. The risk of the outsourcing maintenance still as one of the factors affected the safety requirement. So the safety requirement, ICAO organization and IATA and Aviation Federal Administration always introduced the new regulation to avoid any mistakes in terms of the human error or design or the maintenance problem to avoid any damage to passengers. Future of work, based on the methodology they use it, we can see the study maintenance scheduling problem, a light maintenance, and the A-check, P-check through the discrete event simulation. The duration between the turnaround process of the aircraft built based on the flight operation types. I explained to you the difference between long haul operation and the short haul operation. That's the key point to use the model to expect the number of the operator need for saving the aircraft. Thank you for your attention. Any question? That's some resource you can use it. That's acronyms. There's some details about the marketing.
Thanks, Salah. Is there any question? Okay, I do have one question, Salah. So, very good presentation and good review on the challenges which normally comes in MRO's scheduling. Now, my concern is that right now we really have a noise beta regarding how the digital engineering is evolving. A lot of maintenance approach being influenced by the recent development due to digitization of sensing and data collection, and also affected the repairs as well. So what do you think that how these challenges which you have highlighted will be influenced by the digitization of the maintenance approaches?
Actually, it's hard. It's quite difficult to answer your question because, as well, according to what I'm saying, ICAO organization and the IATA organization and the Aviation Authority, they introduced the new regulation. They avoid using the technology to expect the failure because before it's happened, but nowadays they not trust to using the technology for the digital or something to expect it. You have the book and you have time sheet. You have to follow it. You will not trust the technology to use it in terms of should the aircraft goes to maintenance in the same time. I can show you. I give you the example for the lean maintenance when it should be the aircraft goes through it. You see my screen? Excuse me.
Here, yeah.
Yeah. So you can see in here, you can't change this because it's come from the aircraft manufacturing. So you have to follow it. If you use it the technology or the digital to expect it for the scheduling, and you try to reduce at the time when the aircraft, yeah, it might be happen, but you have to follow the regulation as you can.
Okay.
Also, okay.
Have you found relevant literature which actually analyze the challenges of MRO
By digital?
with the digitization or the modern change, we may say, in the current maintenance approaches, with the potential digitization in them? Have you seen some papers published in this area?
Is it for digital?
Yeah.
Yeah. To be honest with you, I can answer this question, but now I'm usually I focus about 4 and the 5 factors. I can see the previous some of the paper they mention it. However, when I ask who is a professional for the MRO in the maintenance operator who works in the MRO company in Cranfield, ask him about if you trust for using the digital or the technology to improve the scheduling problem or to solve the scheduling problem. He said to me, nowadays it's become true. They trust it.
Okay, thank you. Any other questions from the audience?
I would say there's a good presentation, and I might suggest for scheduling, looking into algorithms like genetic algorithms, big data sort of thing. It's also proven to solve some of these very complicated issues where there are a lot of interactions, very complex dynamics, which would be the case for an MRO in aircraft operations. I think it's a complicated problem in itself, but it's perhaps worth looking into one of these big data algorithms to help you perhaps come up with other results for your research.
Okay, thank you.
All right, fantastic. If there is no further question, thank you, Salah. Thanks for your presentation. I would like you actually to switch. If you just turn off your video and your presentations, we'll ask the next presenter. So, Isidro, can you just announce the next presenter?
Yes.
Just one thing to add, Mohammed. I think Ali is back online. Should we go ahead with his presentation now or move him to the last?
I think we can just follow the schedule right now, and we'll do it in last.
Okay, fine. Thank you.
Isidro, it's over to you.
Yes, the next one is maintenance optimization model at the equipment level, by who is doing this presentation? We got Keith Rushton, John E, Samir Khan, and Andrew Starr.
I think John has his name, I think. Is John, are you presenting?
He's busy in another room.
So who is presenting this?
I'm just finding that one out. I can't see any speaker for that presentation.
Okay.
1 minute. Mohammed, I think we should go ahead with the next presenter because John is busy in the other room because there is a slight change in the schedule because Ali couldn't present in the first one. So we can go with the next talk, probabilistic renaming useful life prediction based on deep convolution neural network, that talk.
That is by Alex Grenner, isn't it?
No. That is by Ting Jingyao Wu will be presenting and I can see his name. He's there.
Yeah, Isidro, can you actually take it over? I think Jenga will go.
Okay, excellent. So are you ready, Simbin Sao?
It is Jingyo Wu, I think.
Or Jinghua Wu?
Yeah. Jin, are you there?
List of participants. Doesn't seem to be there.
Yeah.
Okay. So out of interest, is Alex in the room?
Yeah, Alex and Ali is also there. So should we allow Ali to start and then Alex as per his time? What do you think?
Yes. Yes, I
Okay.
think we should
Okay.
go back to Ali
Yeah.
then.
Ali, can you just share your screen and start your presentation, please? If you can hear us. Ali, are you there? Have you lost the speakers?
I'm not sure because I can see Ali's name now in the speaker list. So he should be here.
I also can see
Yeah.
Jingyo is also
Yes,
there.
Jingyao is also there. There's some messages there in the chat section. Wait a minute. Jingyao is saying my connection is poor.
All right, so what should we do then?
I asked him to refresh the browser and connect again.
I think not only they refresh the browser, but if somebody is using it in an Explorer, it won't work.
Yes,
You need to go on Chrome.
exactly. I messaged him the same thing.
So can we go with Alex then? I can see Alex.
I think better to maintain the flow. We can go ahead with that one.
Yeah. If Alex, are you there? Can you hear us?
We can do stuff early.
Yeah, Alex. So if you're okay to present your paper, you can go ahead.
Okay.
You go on presentation mode.
Okay, can you see it?
All right, fantastic. That's great. You can go ahead now.
Cool.
Yeah.
Right, so hello, I am Alex Grenier. I'm a PhD student at Cranfield University. My research centers on uncertainty quantification techniques for maintenance planning. So I'm developing an intelligent system that learns from a combination of quantitative equipment data and qualitative heuristic estimates to forecast the level of uncertainty through the in-service life of complex systems. So jumping right into the paper, the technological complexity of modern engineering systems is increasing exponentially, which requires rigorous and accurate determination of the optimum maintenance scheduling, equipment availability, and turnaround time, whilst allowing for overruns and unforeseen costs. These are hampered by increased uncertainties driven by the data quality and availability, as well as the qualitative influence of workers, expert opinion, experience, and environmental conditions that can result in under or overestimation. Complex systems feature a array of multiple sub-elements interacting simultaneously and non-linearly with each other and the environment on multiple levels. Uncertainty quantification in this context generally only considers the quantitative side of which is the measured data. An aggregation of quantitative and qualitative uncertainties is necessary to capture the full system impact, which influences system reliability and therefore the decisions made around system maintenance. To this end, a framework is presented to quantify and aggregate compound uncertainties to be assessed against a predetermined acceptable level of uncertainty. Briefly then on the research background, the uncertainty is defined as the degree of information or lack of information about a given entity. Error is the difference between the recorded and true value of that measured entity, and the resulting risk is the probability of the loss or gain of the value of that entity. Brief definitions on the guide to the expression of uncertainty in measurement, or the GUM, has been implemented for a range of applications in uncertainty quantification, largely describing it in two separate stages, being the quantitative and the qualitative. So type A, quantitative, considers measured data, and type B, the qualitative, considers things like human factors and maintaining performance. These is typically carried out in the assessment in 5 core stages, being identifying what's being measured, identifying the uncertainty sources in what's being measured and the associated distributions, then quantifying those uncertainties, be it through simulation, and then aggregating those uncertainties together and then reporting the analysis results. The GUM often applies coverage factors to accommodate for the qualitative estimates, which can lead to underestimation of the total uncertainty, so can't be confidently applied to dynamic complex systems. Alternative methods include the pedigree approach, which is widely renowned and verified to equate qualitative estimates in line with quantitative data. Expert opinion and knowledge is scored according to predefined criteria to permit quantitative performance and reliability assessment. Estimates are attributed by their geometric standard deviation, or GSD, where inputs fit to the log normal distribution. For the analysis of data from varying sources and measured for different units, uncertainty factors need to be independent of scaling effects present in the arithmetic standard deviation. So we therefore use the GSD as the uncertainty measure, as this overcomes the scale dependency. In order to aggregate uncertainties represented by different distributions, a ratio between the standard deviation and the mean is obtained via the coefficient of variation, or CV, given as a percentage to represent uncertainty. A set of equations are defined in literature, given in this table, to convert symmetric and asymmetric distributions to their respective CVs. The CV can be used as a measure of uncertainty for each input and aggregated to give a representative total. This was the method selected in the paper and applied to the framework, which will be detailed in the following slides. So just a brief summary on that. The majority of the uncertainty or quantification approaches follow the variations of the 5-stage process defined in the GUM, but this doesn't adequately consider the qualitative attributes required for more complex systems. Considerations of qualitative uncertainty are best made through the pedigree approach, where an identification of the most appropriate distribution functions to represent each input is key to assess the uncertainty. The approach described in literature can be used to quantify and aggregate compound uncertainties through their respective CVs, applied to a range of symmetric and asymmetric distributions. So symmetric is normal distribution and asymmetric is a log normal distribution.
While formulae to denote inputs of varying distributions by their respective CVs are defined, a method to aggregate CVs from a mix of the symmetric and asymmetric distributions in a compound manner considering the qualitative and quantitative uncertainties was unclear. This is necessary to establish the compound uncertainty estimate represented by different distributions with a significant level of confidence. So this is a broad overview of the framework. This was developed in MATLAB and consists of 5 core steps. So step 1, similar to that in the GUM, is to identify and group the uncertainty sources as the inputs according to their type, be it qualitative or quantitative. Step 2 then calculates the relevant statistical parameters for each input via Monte Carlo simulation and the pedigree metrics for respective types elaborated in 2 sub-steps. So step 2A considers quantitative data, which is imported into MATLAB and indexed as cell arrays to accommodate varying data sizes. The arithmetic and geometric mean and standard deviation are then calculated, as well as the maximum and minimum values of each input variable. Monte Carlo simulations are then run for the log normal, normal, and uniform distribution types for a predefined number of points, defaulted to 10,000. The standard deviation is then calculated using the simulated data for each distribution type. For log normal parameters, the geometric mean and standard deviation is calculated, and the normal and uniform distribution parameters are arithmetic. Step 2B scores the qualitative factors against predefined pedigree criteria, where the ideal case for these is a minimal uncertainty with a pedigree score of 1, and then increasing scores from 2 to 5 have a progressively higher uncertainties owing to their representative criteria. The scores for each factor correspond to an uncertainty indicator given as the GSD, defined according to the subjective impact each factor has on the system. The GSD is calculated from the indicator values obtained from one or multiple sources. If the uncertainty indicators are obtained from a single source, the GSD is given as the square root of the uncertainty indicator. If they're obtained from multiple sources, then the GSD is given by this equation, modeled by the log normal distribution. Ideally, and especially in the case of complex systems, the definition of the pedigree criteria and related uncertainty indicators should be made by a diverse selection of suitably qualified individuals being expert in the field that they're looking at. Step 3 calculates the CV of each input. In order for uncertainties from different data types represented by different distributions to be aggregated, they must be considered on an equal scale. So these are calculated within the framework by a sequential algorithm according to the specified input and distribution type. Summary tables are then generated for the quantitative and qualitative inputs, detailing key parameters calculated in steps 2 to 3. So step 4 then combines those respective CVs where the normal and uniform distributions have a symmetric, they are symmetric, which, as I said before, the arithmetic mean is equal to the mode, so it doesn't change as uncertainty increases. They can therefore be aggregated additively by the root sum square given in this equation, which is also what's used mainly in the GUM. The log normal distributions are asymmetric, where the arithmetic mean will change as the increasing or decreasing uncertainty, with the increasing or decreasing uncertainty. These inputs are aggregated by the products rule given in this equation. To combine these two with symmetric, to combine the asymmetric and symmetric distributions together, a new arithmetic mean needs to be calculated to account for the shifting uncertainty given by this equation. Then to account for this, the framework splits the calculated CVs of quantitative inputs according to their distribution type. The sum of the symmetric attributes are added to the product of the log normal attributes as given in this equation. This allows the aggregated CV of both quantitative and qualitative data to be determined as a measure of the total uncertainty. The CV is defined as the ratio between the standard deviation and the mean, so the output follows a normal distribution. The uncertainty can then therefore be expressed back as a standard deviation via this equation here. And then step 5 visualizes the calculated and combined uncertainties to assess their comparable impacts on the system. So the visualization will consist of the total estimated uncertainty along with individual contributions via sensitivity analysis. This is widely used to determine the relative impacts of input variables on the compound uncertainty, calculated using partial derivatives. The resulting factors are plotted over the relative total to visualize their impact. These are then given against a predefined acceptable level of uncertainty shown in a color bar on the right of the y-axis, which is again determined in the pre-stages by suitably qualified people, depending on the situation that it's applied to. So that's variable. So applying it in the case study, the heat exchanger test rig here consists of a hot closed loop system and a cold open loop system. This design consists of subsystem modules housing component and fluid interactions that interact in a non-linear manner. This, as well as the subjective opinions and actions of operators, influence uncertainties in the assessment of the system performance and the heat exchanger itself. The oil temperature at the inlet and outlet was measured using infrared thermography. The thermodynamic analysis involving oil viscosity and temperature decrease through the connecting pipes wasn't considered here, as it was thought to be too in-depth into the system and not for the whole broad scope, so it's out of scope for this application. The recordings were taken once the system had reached the operating temperature at 80 degrees C and steady stated, and then 6 sets of 10 recordings were made manually for each parameter with 20-minute intervals between each to let the temperature come back up to 80 degrees and reset. To enable effective heat transfer, the air blower must be in operation, which created an air blanket around the heat exchanger unit, disrupting the temperature measurements for the camera. All other parameters were recorded via inline analog dials. Many of these gave readings on different interval scales, varying the measurement accuracy and therefore resulted in an increased uncertainty. So applying the framework to it, step 1, we identified 6 quantitative parameters and 5 qualitative factors. These included the temperature of the inlet and outlet, T1 and 2, given by the infrared camera, modeled by the log-normal distribution, as the fluid temperature decreased once it reached 80 degrees C, it started to decrease down until the heat came back on and went back up to 80. So the mean was shifting for all the recordings, which gave a skewed result with a slightly different mean for each reading. The temperature reading given by the inline dial after the heat exchanger as T3 was modeled by the normal distribution, as the higher reading interval gave a more constant mean through, though with a greater spread in the standard deviation. And the oil pressure passing through the heat exchanger at P1 was also modeled in the normal distribution, and the blower temperature at T4 and the oil pressure post heat exchanger at P2 were modeled by uniform distributions, as they were constant throughout the recordings. The 5 qualitative factors modeled by the log-normal distribution were the measurement reliability, basis of the estimate, the reading accuracy, environmental conditions, and sample size. So step 2A, the quantitative statistical parameters given by the recordings and Monte Carlo simulation are summarized in this table. The reading intervals and errors given in the columns 2 and 3 contribute to those qualitative factors, which are given in this predicate criteria. These are given in the appendix of the paper, because it's a bit too in-depth to go through now. These correspond to these uncertainty indicators. For the heat exchanger, the uncertainty indicators were obtained from a single source, so their geometric standard deviation is given as the square root of the corresponding indicator. So you can see there how the uncertainty increases with increasing pedigree score. For each factor, it's slightly different. Step 3, the summary tables with calculated CV for each input are given for the quantitative and qualitative factors respectively, calculated using the equations shown earlier. And then step 4 and 5, the combined CV of each distribution is shown in step 4, which is aggregated for the symmetric and asymmetric distributions to give the total for the CV. And then step 5 on the right, the visualization shows the CV for the quantitative inputs in blue, the qualitative in orange, against the aggregated total in green behind them. The color bar over on the right represents the acceptability of the relative factors according to predefined scales. So that can be customized before it's run through the analysis, or once all the data's in, you could then change it again and see how the results change. So further development of this will allow the results to be compared through a proper sensitivity analysis. So on the discussion side, the framework was designed to enhance the system performance assessment through the quantification and aggregation of compound uncertainties. These arise as a result of different recording methods and assumptions made about the system and are modeled by different distributions. The use of the coefficient of variation to represent uncertainty enabled the effective quantification of these compound uncertainties. Previous work in the same area has enabled the aggregation of individual quantitative uncertainties with qualitative uncertainties through the pedigree matrix. The capability to aggregate uncertainties through different distributions is further developed in this paper through an indication of factors that lie outside of acceptable levels, as well as a function to allow the user to view and select the best suited distribution for each input. The acceptable levels of uncertainty are user-defined according to the application and visualized by the color bar. And the benefits of this framework include enhancements to performance assessment and corresponding maintenance planning for complex systems and respective subsystems. Further development of the framework is required to allow for determination of uncertainty indicators for the qualitative inputs given by multiple sources, such as surveys or interviews, rather than one source as was given in this paper. This can be done separately, but ideally an integrated process in the framework will be more efficient. Similarly, a determination of acceptable uncertainty parameters for each input will be performed within the framework. And step 5 of the framework requires further development to determine sensitivity coefficients for each input. Correlations between each input will also be accounted for, as well as forecasting of quantified uncertainty through the in-service life. And that is in another paper that I've done for a previous conference published soon. The heat exchanger test rig, since doing this work, has been upgraded to resolve the issues in the flow rate and in the temperature reading through the air blanket. We've put in a new centrifugal pump, so rather than having an air-operated pump that we had before with a varying flow rate, it's now constant flow rate. And we fitted digital temperature and pressure sensors using the IO-Link interface. And this will improve the data quality and allow for more consistent recordings to be made for the uncertainty assessment. So that's it. Thanks for watching and taking the questions.
Thank you, Alex. Thanks for your presentation. Any questions from the audience? Feel free to ask.
There is one question posted under the general chat option by Salah.
Oh, that is actually for the previous one, I think.
Yes.
That's not actually.
Okay.
Alex, if I ask one question, it's a very nice presentation. Overall, very good project seems to me. You managed to have different distribution functions to fit the data and then quantify the uncertainty on behalf of that. Most of the industrial systems, when we actually go, not most, but quite a few, they do generate the parameters of sensing or whatever the tool you are considering to measure. Sometimes it happens that you have very stochastic data, right? and it's hard to fit with any kind of fitting, right? So what do you think, how you will quantify the uncertainties for those cases by using this framework?
Well, looking at some other applications as well for developing for it and different distribution shapes, and where you have highly stochastic data, they somehow must fit some kind of distribution, but there are certain types where you could say split the data to say up to this point it fits this kind of distribution, and then further into the future it changes. So the idea is to model the uncertainty through in-service, like applied to equipment level, so looking at availability of certain equipment. So rather than specific sensor data that records over, say, like certain time intervals and gives you really stochastic data straight out, it will look at, say, like over a period of years or months, how does it change that way, which should give a better kind of distribution. But if it is really sporadic and doesn't really fit to anything, then I think there are distribution types that can be put into the framework, and we can adapt and develop it that will suit that. So things like maybe the Weeble distribution or the beta distribution to something similar as well.
Do you expect that
there are other types that could be fed in and developed in further?
Do you expect that rather than having, it's good to have all this distribution, but if you can add a bit of clustering here for trained your whole framework, that
so the AI side comes into the forecasting as well. So I'm looking at using LSTMs at the moment to do the forecasting side. So something like that with an AI base to do the initial quantification as well would be definitely useful. Something to think about in the further development.
Okay, great. That's great. Okay, any further question?
I do have a question.
Yep.
How would you validate and verify a framework like this?
So I'm going to compare it with other existing methods, such as the the Fourier transform, the FAST method. Other existing strategies that look at uncertainties like this, and compare it also to like the GUM method, where if we don't consider the qualitative factors so harshly, if it's only quantitative factors, you have a different kind of uncertainty measurement. But then also talk to people in industry and say, if you consider more of these qualitative factors, will that help you enhance your uncertainty assessment? Looking in industry, and also just seeing what other methods exist already. So like the method that I developed here using the geometric standard deviations, how my results compare to their results. And then the question is, how do I know which one's better? And that would be then considering the same kind of data sets and seeing what kind of uncertainties come out of it.
Is there a perfect machine, like a benchmark you can use?
I think the answer is no. There's no perfect case for uncertainty, because that's the whole nature of it, is that it's uncertain, which makes it tricky. But I think that's when it comes down to validation of uncertainty, you just got to look at how do other people look at uncertainty, and how can you compare that with like expert opinions. You'd have people that work with uncertainty every day in industry. How do they do it, and how am I proposing new methods to do it? It's a tricky one.
Okay, thank you. There are no more other questions. I don't see any other questions in the chat.
Yeah, no, nothing here. If there's no further question, thank you, Alex. Thanks for your time. Thanks for your presentation. Right.
Thank you.
What's next, Ajit? Are we having Ali?
John has joined in the room, and also I can see Ali is present. So I asked him if Ali can present whether his connection is good or not. So you can ask Ali to present now.
Ali, are you there?
Yes, I can hear you. Can you hear me?
Yeah, I can hear you. Is it possible to you?
Okay, I didn't have any connection problem. I don't know what happened. Yeah. I'm so sorry.
So give a try again, and if it is working, then you can go ahead with your presentation.
Yeah. So can you see my screen?
Something is coming up.
Yeah, it's uploading now. It's still not. I can't see it. It's still black.
Okay.
Yes, we can see your screen now.
Just for your feedback. Okay. So I'm sorry for the problem.
We just lost you, man. Okay. I think we lost him again.
So the topic I will talk about today is investigating the impact of human in the loop and in digital twin in industrial maintenance control. This is part of the digital. So I will try to be brief due to the problem. So this is the outline of my presentation. I will go quickly on the motivation.
We lost him.
Yes, seems to have problems with.
Yeah, still has problem with the net.
I think he's having problem with bandwidth.
Yeah. So if John is here, John, can we start with your presentation, John?
I'll share my screen.
Yep.
So this is maintenance optimization model.
Correct.
At the equipment type level.
It seems that I have a problem. Once I share the screen, I lose the connection.
Ali, can you just hold a second because we are moving towards the next presentation with John, right?
Sorry again, I can't hear you. Sorry.
I'm saying just hold a second because we are moving with the next presentation with John Arkenchu. He's presenting his presentation right now, right?
Okay, thank you so much. Okay.
John, you go ahead.
Okay, so I'll make a start. Hello, everyone. I'm John Arkenchu. This paper was prepared in collaboration between Cranfield University and the Ministry of Defense. So Keith Rushton from MOD ESCID team was cooperating on this paper. So the title is Maintenance Optimization Model at the Equipment Type Level. So what I'd like to cover in this presentation is firstly give you an introduction to explain the challenges that we're facing in this context, and then take you through a process that we developed that really is trying to model the maintenance plan in a way at the equipment type level. So from there, I'll just give you an example with the validation that we did for this, and I'll finally conclude on that. So the introduction. So ultimately, when we look at major assets, we're really trying to understand for every pound that we spend, how much equipment available days will we have. So this is really about measuring the amount of availability, operational availability that we may get. So how we can achieve this is really an important question. So in this paper, what we're really trying to explain is how do you trade off between the preventative maintenance, so PM stands for preventative maintenance, and CM, which is the corrective maintenance. So that's the kind of focus for this paper, so that we can trade off across these different maintenance strategies, come up with an optimized approach whereby we can determine the money spent versus the performance outcome that you're going to get. So in terms of maintenance, if we look at maintenance, in any system, we would ideally like to minimize the total maintenance costs, and we would like to maximize the system availability. Now, these two things are not independent from each other. So from that perspective, we need to optimize the total outcome that we're interested in. Another third aspect, which is really also important, is safety. And I think, based on the discussions that we've had today, another aspect to start to consider much more is around the sustainability outcomes. So the environmental impact is also another aspect which is becoming much, much more important. So along these lines, with equipment type level, what I'm referring to is trying to move away from component level analysis to a level higher, whereby maybe we're looking at systems. It could be like a gearbox, it could be a major part of an asset, where we're defining that as the equipment type. So that gearbox, for example, could be part of multiple equipments. It could be present at different stages across the life cycle. So we're trying to have a good balance between bottom-up and top-down approaches, and it's really trying to simplify and improve on the efficiency of decision-making. So in terms of availability, the way we defined availability in this paper was looking at uptime over total time. So the total time was defined based on uptime and the downtime. And we defined these as the mean time between failure, so MTBF, and the mean time to repair, as well as the downtime. The more detailed description of availability could be defined based on things like logistics and administrative delays. So you can add that as well into the equation, whereby you've got things like operating time, standby time, total preventative maintenance time, total corrective maintenance time, and also the administrative and logistics delay time. So there's various ways to define availability. Now, what we try to really understand with the different types of maintenance requirements was that, firstly, we wanted to look at the failure patterns. So P in this figure is really stating the probability of failures, and T is time. So over time, there can be different types of equipment failure behaviors. So the top one here is illustrating that in terms of the probability of failures, you may not have any overlap in terms of the likelihood of a failure taking place from one failure event to another. And in that type of context, you could just apply a purely preventative maintenance strategy. So this means in this type of environment, if you were applying any corrective maintenance, then it wouldn't actually add value. The other extreme is purely corrective maintenance. And what you can see here is that there's a lot of overlap from one risk or one failure probability to another. And this overlap is really highlighting that if you did preventative maintenance in this type of context, it actually won't really add much value, because the risk of corrective maintenance requirements isn't going to be decreasing. So in this type of environment, it's probably more useful to just have a corrective maintenance-based approach. Now, we also have the scenario where there's some level of overlap, but not necessarily as much as the purely corrective scenario. So in this type of context, you have a mixture of PM and CM. So if I compare these three different scenarios, probably the highest area that's maintenance is applied is where PM and CM is overlapping in this nature. So in terms of how we can quantify this, we're using the mean time between failure and standard deviation as the metrics to be able to understand the level of overlap that there is. So as the amount of overlap increases, then we're expecting purely a corrective maintenance-based approach. So that's the key kind of logic to what we've developed in this paper. So to continue, if we look at the corrective maintenance resources that are needed, there's various things that are used across any corrective maintenance type activity. So we need people, we need spares, we need information, we need test equipment, and we need facilities. So across these different kind of resources, we also need to think of the different levels of these different levers. We need to understand so how many we need of these, at what kind of scale should they be. So is it a technician? Is it a project manager? The different kind of roles. And we also need to think of the location. So the location also is referring to how many at different places with different kind of roles, responsibilities do I need of these different types of levers. So in terms of the process that we built to trade off between preventative and corrective maintenance, we have 4 major steps. So step 1 is really trying to define a rational range for the time between preventative maintenance. So the logic for this is really saying, if I change the amount or the frequency of the preventative maintenance activities, then we can start to see if there's any impact. So we're really just shifting the time in terms of how frequently are we going to conduct preventative maintenance activities. So then we're looking at the failure rates associated to that. And then we're looking at the corrective maintenance costs for each failure rate. And lastly, we're really trying to minimize the total cost. And in this process, we're doing the trade-offs for total cost minimization. We're also doing the trade-offs for the availability maximization. So ultimately, we're identifying a zone of interest for the different types of maintenance or different type of maintenance that we want to conduct. So in terms of the case study that we applied, so we looked at a defense-based case study, which was looking at land-based vehicles. And here, the data that we had was that the mean time between failure using a normal distribution was 12.5 days. The standard deviation was 3.1. And that meant every 3.1 days, we have the risk of a failure taking place. Then we had the planning period, which was the project duration, which was 46 days. And then we also looked at the fleet size, which was 187 equipment types in this. And then we defined the average cost of one corrective maintenance action. And this was £5,000. And the important thing here is that you could use multiple projects or you could use historical information, but we're using specifically the average across all those different values that you have. The other thing was, again, the average time of conducting one unit of corrective maintenance action. So for this project, it was half a day. And then we also looked at the average cost for one preventative maintenance action, which was £500. And then we looked at the average time of one preventative maintenance action, which was 1 day. So from there, we could calculate whether this is a PM and CM policy, or if it's just a CM policy, or if it's just a preventative maintenance type policy. So based on the data that we had, we realized that a combination of PM and CM would be the logical approach for this, because there's some level of overlap between the different likely failure outcomes. So from there, we realized that we will spend some days in PM and some days in the CM activities. And what you can see here is that of the total days spent in maintenance, which is 6.7, a very large chunk for this project is spent in the preventative maintenance activities, and quite a small amount is spent in the CM activities. And I guess one major reason for that is the amount of cost for CM is so much higher than the PM activities. So that was one reason. And then we could calculate the total cost of maintenance. And we first calculate it based on one equipment type. Then we could calculate it for the whole fleet along those lines. So then the other kind of results that we produce here is that we can define the trade-off between the PM and the CM. And you can see that the green line here is illustrating the total costs of maintenance. The blue line is showing the PM costs. And as the time between the preventative maintenance days increases, you can see that the PM costs are decreasing. And in parallel, your corrective maintenance costs are increasing, as shown in the red line. So what we were really looking for was finding the optimum point for the total costs. And you can see from here, we can then start to identify the amount of preventative and corrective activities and costs that we're going to incur. There's a similar logic for the availability side. So in the chart on the right-hand side here, you can start to see how many days are spent in different types of maintenance. And you can really start to compare the amount of time that's spent in different types of maintenance. So this was one case study that we applied it on, and it gave us a good indication relatively quickly. You can see the amount of input that's required is relatively low, and it can give you a quick insight as to how to develop a maintenance strategy. So just to continue in terms of the optimization, so we could define the cost outcomes, and we could also define the availability outcomes. And I think one of the good things here is that we can also define these in terms of a 3-point estimate. So the minimum, maximum, most likely outcomes as well. And that way you can start to understand how much uncertainty there is with the data input and how reliable the outcomes are going to look like. So just to conclude, so here, I think one of the kind of gaps that we tried to fill was really looking at how can we move away from specifically component level analysis to a level higher, whereby we want to develop a maintenance strategy and we want to develop that in a very effective manner. So for us, it was about creating a process whereby we can trade off between the costs and the availability. And then we can also start to define a strategy in terms of the maintenance activities to meet the cost and availability targets. So for us, because we moved this to a higher level, we then could influence the budget allocation processes, and we could really help with defining how the project at a high level can be planned. So it also gave us a process really to optimize between the preventative maintenance and corrective maintenance allocations. So this means that over time, you can start to define what are the different activities and resources that are needed to deliver a maintenance strategy. Now, in terms of future work, we feel that further work could be done, particularly around understanding risk and uncertainty in maintenance delivery, and really understanding how over time the risk and uncertainty changes can be embedded into the maintenance plan. So for us, there's more kind of dynamic processes that are needed to quantify the impact of risk and uncertainty. So with that, I'll conclude and thank you all, and I'll be happy to respond to any questions.
Thank you, John. Thanks a lot for your presentation. Any questions, please?
I don't know if Keith is in the
Participants?
yeah. Keith, if you'd like to add anything to the presentation, please.
Keith is there, I think. Yep, go ahead, Keith.
Added you as a speaker now.
Yeah, that was good. That was a good capture of what's actually happened. What that we've really found is because it's at an equipment type level, this will work for any type of equipment in any of our domains. So air, land, sea, joint space. It's the same process, and that's an absolute killer scenario to have the same process applied to what superficially look like very different equipment support worlds. So that's commonality of process is absolutely critical in what we're trying to achieve at the MOD. And as John says, it's about trying to get the right money into the right space to fund the right activities to achieve what our clients, so in our case the Army, Navy, Air Force and Joint Forces actually need. So this gives us a real useful, quick is the word, insight, quick and dirty insight into what the support arrangements should roughly be before we make any commitment to go into any level of detail. So it's absolutely critical, and it's actually already generating significant financial and availability benefits wherever this is applied, which is pretty much all equipment these days. So yeah, it's been very, very beneficial. So as UK taxpayers, we're saving a fortune. Well done, everybody.
That's an
Thank you.
advantage. Yeah, that's an advantage.
It's a good presentation. It's a good input. Looks like it's been successful in applying this research. I have a question in the sense of, could this be validated, say, next fiscal year, say, comparing what the model, what this research proposes, and then at the end of the next financial year, compare whether it makes sense, and how much is different to what you expected you would save, for example. I think that would be quite interesting.
Yeah. So that's ongoing, Isidro. So the utilization of the equipment, we're rolling out a process across the whole of the Ministry of Defence for all equipment basically over the next 3 and a bit years. So this process will provide a significant pool of data sets to further enhance the validation, and of course build in the continuous improvement stuff that John's mentioned. We'll be able to do that and to quantify it in terms of pound notes and availability as well. Because don't forget, it's a bit of a moving feast, because it's not always the case where we actually need more availability, because the demand requirement for the equipment goes up and down. But this methodology will cope with that, because you basically set your target and then you're looking for the solution that meets those conditions. So it has utility past what it superficially looks like is the only way I can actually explain it.
No, it's great. I think it's good.
But yeah.
Just a curiosity, actually, from my side, what the MOD was actually using before this model, for example, how they actually do a trade-off.
It was this and plucking stuff out of here and runes and chicken bones and so what's happened, so the world of ILS, integrated logistics support, has a fantastic history in the MOD, and people have actually said, oh, so this is a bit like doing ILS properly then. Correct. So it's provided the thing with the ILS stuff. It was historically sort of done at the beginning of a life cycle and then never touched again because it cost too much money. There was too much resource. So as soon as any sort of financial constraint went, that process went. And it was done as a one-off box ticking exercise, job done, without understanding the impacts in terms of the through life. So this process is part of, and John showed you some of the other levers. It's one of the levers that we utilize. Prevention versus cure, which is the best solution. It is one of the first decisions, and then it goes into further detail, which we have worked up as well. But it's starting to introduce that an affordable way to do ILS practically and properly, i.e. all the time, because as I said, the demand requirement goes up and down. Traditional ILS, as done by the MOD, was everything was a straight line for the next 40 years, which is clearly barking mad. But nobody queried it, because it was easy to calculate if everything's a flat line. And similarly with the budgets, the budget sort of went up like that by 10% every year, and then somebody took a bit away, and then somebody added a bit. It's a bit chaotic, really. So what this has done is introduced a significant logic to the whole process. That's not only and I'll get off my soapbox in a minute. It's not only logical to engineers; it's logical to the business side as well. So this is connecting engineering thinking to the people who actually make the financial decisions about where the money is spent, and that's a true TES requirement, to actually join up the business and the engineering side for both non-engineers and non-business people, connecting together to actually make the right decisions. That's the real utility of this stuff. And it's bearing quite significant fruit, actually. So yeah, it's been a very, very, very good success story, actually.
Fantastic. Thank you, Keith. Thanks a lot. Thanks, John.
Thank you.
And now, Arjit, do we want to wrap this session up, or do we have to give it last to Ali?
Yeah, last try to Ali, we can try. I just received his slides as PDF, so I can play the slides on his behalf, and then he can present via audio.
All right, fantastic. Ali, are you there?
Mohammed, are we also missing a presentation?
Yeah, Jingyao, he is not responding at this moment, so he's saying VPN. Through VPN he was trying to connect, but somehow the internet connection is bad and he cannot connect.
Sorry, I just wanted to make sure we're not missed anyone, because we're
trying to catch him and try to make some amendment for him, so we're trying.
That's all right, as long as we don't leave anyone without presenting.
Yeah, of course.
Ali, can you respond us? Are you there? Is he on the speaker list, Arjit?
He is.
I can see his name. So he just sent me his presentation through PDF and said that maybe he can present through phone. I said, I think you have to connect through Remo by phone or something else. Otherwise, it's not possible.
Okay, if you just give a shout to him on his... Do you have any contacts?
No, I was just mailing him. So I just sent him the mail back. I'm not sure. Ali can able to hear us or not. Ali, can you hear us? Or you can, if you can hear us but your voice is muted or something, you can drop us a message. No, I think he's still having internet issues and he cannot connect.
All right, then we're supposed to wrap it up, Isidro.
I think it's we have to do that.
So thank you very much. Thanks for your participation. I hope you have really get very good insight for the papers which has been presented regarding MRO scheduling, uncertainty quantification framework, as well as the maintenance optimization and the last presentation we had. And if you have any further queries, I think on test proceeding website, you have all the papers, and also you have the contact email addresses for each individual authors. You may directly contact them via the email addresses. And that's all from my side. Isidro, you want to add something before wrap up?
Yes, I wanted to thank you all presenters and obviously the audience and Arihit as well for support. Thank you, Mohammed.
Thank you.
Thank you.
Bye-bye.
I have the quick announcement before closing the session.
Yep.
So we are just having parallel sessions in auditorium as workshop, and in room 1 there is another technical session going on. As soon as those are finished, we'll be joining for a closing ceremony today, which will be at I think 5:45. So please, after I close this session, everyone will be sent back to auditorium, and at 5:45 the closing ceremony will happen. I think Pawan is going to say something.
Hi everyone. Thank you for this. We've had a few technical challenges today, as you have noticed. We are currently in the process of scheduling them for tomorrow's presentation. Hopefully you're able to join us. As of now, we are wrapping this session up so that you will be sent back to your room, and hopefully this event will end. But there is a live session in the workshop. There's a workshop session happening in the auditorium. Please join us there. We will be concluding today's event at 17:45. We've got final words, closing remarks for day 1, and we will reconvene tomorrow morning. So if you could join us up when we get out to the main floor, please could you join us in the auditorium? Thank you.
All right.
Yep.
Bye-bye.
All right.
Thank you.
Thank you. Bye-bye.
Thank you.